All right, so I guess we're good to start. So we have some ground to cover today. So we're doing recurrent neural networks. So you've had like 4 lectures about that. So I'm not gonna do so much recap because you're supposed to be on the paper, you're supposed to be familiar with them. You know that they have infinite memory, so you use them to handle sequences. It can be sequences of any kind, but in particular in language-based tasks, in translation, in speech, in practically everything. They're the basis on which you build everything. You also know that they're not perfect because they're hard to train because of all the gradient issues that are all the more important with RNNs because they're once you unroll them, they're extremely deep. They've got weird loss surfaces. Also, you might not know that yet, but dropout and RNN kind of don't work well together. You have to find tricks to make them work. So you know that STMs and GRUs are meant to solve some of these problems. For example, the exploding gradient related issues. But I mean, it doesn't always work. So like when you use RNNs, you have to try a lot of stuff, look online for solutions adapted to your particular problem, and think about it quite a lot. So you knew that. What you may not know is that in addition to that, RNNs are not so easy to implement either, compared to the rest, I mean. So you've done MLPs and convolutional layers. RNNs, because you handle the sequence, with the batch you have 3D inputs, and it can be a little tricky to manage. So we'll try to cover mostly that today. So there is a notebook for the recitation. So try to get your hand on it for when we're going to use it. So the plan for today. First, we're seeing a bit language models. I don't think you've seen that in the lectures. There was a lecture for that, but if I recall, it was skipped because there was some delay with the beginning of RNNs. So we'll have to see that because it's very important for homework 3. We'll see how to do RNNs in PyTorch in practice, how to train, how to use them to generate texts. And in the end, a bit about variable length inputs, because but you'll understand better what it means when we come there. So, any questions up till now? I guess maybe not. So, sequence-based tasks. You've seen these diagrams in the lectures. When you're dealing with sequences, there's a lot of possibilities. You can have a sequence in input and try to have one output. Like when you're doing sentiment analysis and you feed all of your sentence and you want to know what's the color of the text in terms of sentiment. You have the one to many tasks, like when you feed an image and you want to get a sequence of words that describe the image. You've got the many to many tasks when you have a sequence in input and you want a sequence in output. So you've started seeing in speech the CTC part where you don't have as many outputs as you have inputs, and there is a lot of work to how to do that well. But in other cases, simpler, you have exactly one output per input, but for each output you want to use all of the past, the one on the right. So you can do that for part of speech tagging, for example. Now, language models, what are they doing in all this? Basically, a language model is a component of NLP systems that gives you the probability of one sentence with conditioned on nothing. So it's probability in general, so to speak, which doesn't seem to mean much, but basically you can see it as an indicator of how likely your sentence is to be a real sentence. Like it can mean, well, depending on what you train it with, it can mean whether it is fluent or whether it is grammatically correct or whether it is within the topic of the document you trained the language model on. So you can use that like for fluency assessment in machine translation, for example. So you can see that also as unsupervised learning, which has not been done yet in the course. So it's kind of your first language unsupervised neural network task. So to train it, we're going to turn it into a supervised task where it becomes a many-to-many task. So basically, if you want the probability of a sentence, so a sequence of words, E1, E2, up to EM, you know that you can decompose the probability in like probability of E1 times probability of E2 given E1 times probability of E3 given E1 and E2, etc., up to EM conditioned on all the words before EM. So thanks to that, you actually now have a sequence to predict. So you can from first predict E1 and then predict the probability of E2 given E1, etc., etc. So you end up having E1 up to EM minus 1 as your inputs and E2 up to EM as your outputs. And the good thing is, since it's the probability you try to predict, cross entropy is going to work very well for that. So you'd get an input like this, or you feed successively, like here it's a y, so it goes. So you feed the y1 up to y9, and you try to predict y2 up to y10. And in the middle, you've got your RNN in green. Before that, you have a projection layer because your words are represented by integers, usually, that are their indexes in the vocabulary. So you project them to a vector, an embedding vector that represents them. You feed these vectors to the RNN, and the output, you apply another linear layer, and you get scores on your whole vocabulary, and you use these scores to do cross entropy to predict the output words. Is that clear until now? Yeah?
The W2 that outputs the same one that's being fed into the second one?
Yes, it's the same. So when you're in training, you use all the words up to the one before the last one is in as input, and all the words from the second to the end as the output. Yes. All right, so just out of curiosity, like RNNs can do that pretty well because they have infinite memory. So when you want to predict EM with respect to everything that was before, you need to know everything that was before. So you need infinite memory for that. But when you don't have that, you usually use the n-gram assumption, which if you've done any NLP, you know what an n-gram is. If not, it's just a tuple of successive words of finite length. So a trigram would be EM minus 2, EM minus 1, EM. So in the n-gram assumption, you consider that the probability of a word depends only on the probability of the n minus 1 words before. So you can do a lot of stuff with that. It works well too, actually, better than you'd expect. But recurrent neural networks can have brought the use of like long-term memory in this area, so they've been pretty useful. Another thing you can do, like with something like this, is just you count the words. That's what the n-gram models are. So when you have EM minus 1, EM minus 2, you just look at what's the word that appears the most in the text after these two words, and you basically predict that. So these are not probabilistic. Yeah, they are probabilistic models, actually. You could also do a multi-layer perceptron where you look at like the finite window of like the n-1 previous words and you predict the next word. But recurrent neural networks are, so to speak, better than that. Not always, but they help a lot. So how to do that in practice? For RNNs in PyTorch, you've got modules like you've got for everything else. So in the NN set of classes, you've got an RNN class where you can precise the input size, the hidden size, the number of layers. So that's if you use like stacked recurrent neural networks, like you should have seen in the lectures, vertically stacked. You have an option batch first, where you basically you say if when you feed the input, you want it to be first the batch dimension, then the sequence dimension, or the opposite. If you think about it, the opposite kind of makes more sense actually, because if you're dealing with a batch, you're gonna feed the batch for the first word first, then the batch for the second word second, etc., etc. Dropout. Dropout is not for the hidden state of the network, but between the layers. So if you use a recurrent neural network with just one layer, dropout will not do anything. And bidirectional, you know that one because you've seen bidirectional networks. So you just have a network in one sense, a network in the other, and in the end, the output is the concatenation of both. So the forward method, you will take an input that's dimension would be if batch first equals false, length of the sequence times batch size times input size. And it's going to return pretty much the same thing, but with the hidden state instead. And you have to feed the hidden state too. That's extremely important. So in the RNN is going to deal with updating the hidden state at every step, but you have to feed the first one. So if you don't feed anything, it's going to use a 0, which is reasonable for the beginning, and then it's going to update it, and it's not going to be 0 anymore. And in the end, it's going to return both the outputs of the size similar to the shape similar to the inputs, and the hidden state at the last step. Yeah.
Is it possible to train the initial hidden state?
You can, yes, if you have like another class around your network, you can you can define a vector as like a parameter, and then you use that to feed your network, and it usually kind of helps. So you're right to precise it, but you cannot ask the RNN module to do that for you. You have to define it yourself. So the one thing you know is that the output of the network is at one step is exactly the same thing that what is if you go there, yeah, what's in the horizontal lines for the RNN is actually the same thing as what's on the vertical lines, and it's updated at every step. So in terms of this RNN module, it's if it returns like the outputs y and the hidden state h, actually y of at the last index, so at the last time step, is equal to h at the last layer. The -1 is because the hidden state has you've got as many as you have layers in your network, so it's h -1 too. Is that clear for everyone? So for LSTMs and GRUs, it's basically exactly the same thing, with just one difference, which is that when the LSTM returns the hidden state, instead of being like for RNN, it would be a vector, a tensor of shape, number of layers times batch size times hidden size. For the LSTM, it returns both the hidden states and the memory cells. So you have a tuple of these things. Now, there is an alternative that you can use if you want to basically control what's happening inside of your recurrent neural network. Because here you feed the whole, previously you fed the whole input sequence, you got the whole output sequence. If you want to change stuff in the middle, for example, you want to add some kinds of dropouts on the hidden states, or you want to access the hidden state at the intermediate layers or whatever, you've got a smaller thing. That's the RNN cell module, where it takes an input of size batch size times input size. It takes the hidden state of size batch size times hidden size, and it returns the hidden state at the next step. So basically, with an RNN cell, you can recreate by yourself the whole RNN class, or you can do stuff with it to make it more suited for what you want to do. So it becomes, for example, extremely useful if you're using something like attention, like that you'll see later, or for many situations. But if you have the choice, use the other one because this is much slower. And you've got also an LSTM cell and a GRU cell to use. Now, if you look back at the language model, you had a projection layer before the RNN and a linear layer after that to do the scoring of the output words. Hey.
One question.
Yeah.
You said slower, but is it slower in terms of computation or just like programming time?
Well, both actually. I was meaning computation. Like PyTorch is optimized so that when you give it a sequence, it's gonna do what it does on the GPU. But here, if you feed it like time step by time step, it returns a tensor every time. So you know that it uses C as a back end when you do computation. So it's gonna do C and then Python and C and Python. So it's highly less efficient than just feeding the sequence and letting PyTorch do its thing. And also, it's slower to do because you have to do everything. So, yeah. So after the RNN module, you'd stack a layer that takes the hidden size and predicts your vector, your vocabulary words. So you'd have like, yeah, linear layers. So hidden size as the input, vocabulary size as the outputs. And on that, you can do cross entropy like you usually do. And before that, you need another layer that's gonna take an integer that represents your words and is gonna return its word embedding that will be a vector. So you've got the embedding class that does that. So everything it does is actually like it's got a matrix of weights, and when you give it an integer, you get the vector at the index of that integer, and that's pretty much it. So you could use a linear layer to get the same result by feeding it with one hot vector, but it's more efficient to do it this way. And you can feed it with something at the shape as you want, and it's gonna return something of the same shape, but with the embedding dimension additional. So we'll see an example in the notebook later. Now for training, you know that like if you want to train, you need to you have your text. You want to extract batches of this text to do your training on. I don't know what time it is. I'm just gonna keep that. Oh, okay. So one way to the most simple. So if you do that, if you can do that, you've got your initial raw text, and you can divide it into just if you have it like as a one concatenated integer long tensor. You can reshape it to have all the sentence length L sequences, and you basically can use these sequences of fixed length as your inputs, and it's each one is an input sequence of size L. So if you do that, even if you just do that on paper, your network should be able to learn how to deal with sequences in general. So maybe it's going to use memory that doesn't use the whole sequence, or maybe it's going to have trouble using more. But if you take a length, long enough sequence length, that should not be a problem. And so that's basically how you get a batch. So we'll see later that it's not always that simple, but for language model, it works pretty fine. Now, you need to do your training, and you need to evaluate how good you are to know when to stop. So to do that, you can look at the cross-entropy loss. But if you look at the loss per element, actually it's the sum of the loss for all of the words of your sequence. So it's hard to know when you look at the loss that that's proportional to your number of words to know if it's good. So usually the metric you use is the loss per word. So you divide your loss by the number of words in the sequence. And another metric that is very used is the perplexity, which has a complicated meaning, but in the context of language models, it's just the exponential of your loss per word. And the perplexity kind of evaluates how confident your model is that this is an actual sentence. So you can, depending on the context, you can know this is a good perplexity, this isn't. So in the homework 3 part 1, we're gonna give you some text and we're gonna ask you to make a language model that reaches some perplexity. So I think we've got enough to look at the code a little bit. So you have access to that, right? I think it's on GitHub. So you import all the models as usual. We'll see this one a little bit later. Now for the corpus, we're dealing with a data set where you got everything that Shakespeare ever wrote, all concatenated. So we're kind of learning to do Shakespeare today. We're going to do a pretty bad network, bad language model, and later in the homework, we're asking you to do a good one. Not on this data, on something else. So I'm not going into the details of how you use this, you get this data, but basically I can read the corpus thanks to the auxiliary file. There's 5 million characters. Oh, by the way, that's important. I kind of assumed we were dealing with a sequence of words. You can do pretty much the same thing with the sequence of characters. So that's what we're going to do today. So that makes sequences longer, but also dependencies more simple. So to know if that's more suited to your problem or not to do character or words, you kind of have to try both usually. So today we're doing a character. Sorry? Zoom? I can try. Better? Okay. Perfect. So here that's the length, the line that transforms a corpus of text into integers by extracting the characters, using a dictionary to associate an integer with each one. Here I transform the whole data set into an NumPy array of integers. And I've got also a method to transform back a sentence into text. So that's pretty much all there is to it. So I made the little text dataset class where I basically implement the things I've mentioned before. So you feed it a text, you give it a sequence length, and it generates your length this sequences in the data attributes. And when you want to get an item, it's going to return both the input and the output. So I mean, and the labels. So like I mentioned, the inputs are everything except the last word, and the outputs are everything except the first word. Oh, and there is a collate function. So I don't know if you've manipulated that before. The collate function says whether how you create a batch, basically. So I made one here because I want to have, if you don't do that by default, it makes a batch by just concatenating all your words and adding the batch dimension first. But I wanted to have the sequence dimension first, so I made a function. And you can feed this function as an argument into your data loader later. So that's what I'm going to do. So see, instead of adding a first dimension and concatenating on that, I add a dimension at the end, and I concatenate on this. So I get sequence times batch tensor of long tensor. There you have the actual language model class. So I've got the arguments are the vocabulary size, the embedding size, the hidden size, and the number of layers too, for the number of layers for the stacked layers of the RNN. So I just keep that. Here's the embedding layer. Here's the RNN layer. So here it's an LSTM. By the way, here's a little trick. People tell you that GRUs and LSTM are suited for different things, and you kind of have to try both. Honestly, it's always LSTMs that work. I mean, probably someone has a counterexample, but like whenever you try LSTM first, and if you have time, try GRUs later. And you've got scoring layers, which is a linear layer, hidden size times. Oh, sorry, I went too fast. Hidden size times vocabulary size. So in the forward, I get a sequence. I feed it to the embedding. Then I initialize my hidden state to nothing. I could just not do that, but it's a good habit to create the hidden size just in case you want to and to explicitly manipulate it. Just in case you, at some point, you actually need to fit something, a specific hidden state. Not here, but like in translation or in speech or anything, you might need to. So I get, from my my input of embeddings and my hidden state, I get my outputs and my hidden states at the last step. To fit that to the linear layer, I have to flatten it first because linear layers can only take 1 or 2 dimensional tensors, and this is 3-dimensional because of the sequence. So that's where the RNNs are actually tricky, is because you have to shift from 3D to 2D in order to move from RNNs to linear layers. Basically, RNNs only take 3D inputs, and every other layer takes only 2D inputs, except the embedding that can actually take whatever you feed it, so that's pretty useful. And so I get my my scores flattened after the scoring layer. So I unflatten it, take back to 3D, size, sequence left, times batch size, times vocabulary size. And that we'll see later. That's to generate text. Any questions on Pontina? All right. So training is fairly usual. The one thing that's important, here I get my input and my output, feed input. The criterion also can only take, Schwarz entropy loss takes 2D inputs, so you have to flatten before that. So alternatively to what I did, I could have just returned the flattened thing here and flattened just the targets there. But yeah, never mind. So flattened output, flattened input, flattened output. I get loss, optimizer, 0 grad, etc., etc. That's the computation of the loss per word, which here, since the input was flattened, it treats the concatenation of all the sequences as one very large batch. So it actually takes the loss is already the loss per word. So you just have to take this loss and take the exponential to get the perplexity. And validation is pretty much the same thing. So nothing so unusual here, actually, if you think about it, up until now. So here are general text and train and validation datasets. Here's the data loader. So like I said, I give it the collate function as an argument. And when I train, so there are just 3 epochs here, you see that the perplexity, and that's why you kind of like it, it's decreasing very fast because it's an exponential. So things that look very slow progress on the loss kind of look good on the perplexity. So it's very satisfying at a personal level. I honestly think that's the only reason we use perplexity actually, but. So we're going from 13 to around, I mean, initially it was more like, I don't know, 100 or something. After 100 iterations, it's 13, and in the end, it's around 4 on the validation set. So that, I mean, there was some progress, so that's pretty good. We'll see later how to actually use that. We'll see it just now, actually. So that was for the evaluation. Everything clear until now? We're going to go back on the notebook anyway. Yeah?
So just to be clear, we are getting text, and then we are turning it into characters and getting the numbers for those characters, and that's what we're feeding into our RNN?
Yes. Exactly.
And then it's outputting, like...
It's outputting...
predicting. Are we just trying to get embeddings for words on the Shakespeare text, or are we actually...
You're not trying to get the embeddings, you're trying to get the actual words. So when you predict, you get something of the size of your vocabulary. So here the whole number of characters, which was 84. So you get an 84 vector that for cross entropy, you just feed that to cross entropy loss. If you want to predict something, and we're gonna come to that actually right here, you just take the Rmax, and that gives you the integer that represents the character you predicted. So since you have a dictionary that associates characters to integers, you can get back the character right after that.
Okay.
Is that clear?
And like, the only reason why it will return words, like, because we're predicting at the character level, is the only reason why it predicts words is because the RNN has some kind of memory about that character goes
Yes.
to the other character. So it's going to return inherently the word that Shakespeare used.
That's pretty much the idea. I mean, that's what we want. And you can do that much with a Shakespeare language model, except writing Shakespeare by yourself. But you'll see that it's when we do generation, it works well to predict words that are actually words. So it manages to do that. But making actual sentences with meaning is much more complicated. But yeah, you're right. If you use an untrained RNN, it's going to return a random sequence of characters that don't mean anything. And if you train your RNN to actually on a text with actual words, it's learning to the dependencies that so that your sequences of characters are actually words separated by the space character.
And so is like a good application of this like text prediction, meaning like I'm typing on my keyboard, and as I'm typing characters, it's influencing what the next characters it predicts I'm going to be doing?
Well, yes. I'm pretty sure it is. So that's like I mentioned at the beginning. I mentioned like language models can be used like more for fluency assessment in translation, for example. You can use them to do prediction, which is what we're going to do, and that can be used completely in an example like that. And more generally, usually a language-based task is you sequence input, sequence output. That's the most general case. So you predict sequence 2 conditioned on sequence 1. So when you do that with the base rule, you kind of have to use at some point the probability of sequence 2, and that's a part that's played by a language model. So basically, they're used for every task where you end up with a text. Either they're the central component or they're an additional or implied component. But yeah, you're totally right. So just like we said, in prediction, like I said, like language models in themselves are not that useful, but they can be used in a variety of contexts. But you can use them to do text generation. So if you just want to predict one word, once you have your logits, the outputs, size vocabulary, you just take the argmax of that, and that gives you the corresponding words in the word case or in character in the character case. Now, if you want to predict, to generate more than one character or word, it's a little more complicated because, like I said, the probability of a sentence is the probability of the product of the probability of each word conditioned on the previous words. So if you can take the argmax for the last words, but it's only going to give you the probability that you want if you fed everything before that to the RNN. So if you're trying to predict 10 words, you have, to predict the last word, you need to have fed the RNN with the 9 words before. So if you want to know which sentence is the most likely, you don't have directly an argmax to look at. You have to feed all the possible combinations of 9 words before and look at the maximum for the 10th word, which is basically impossible, so you don't do that. So you try to get a likely sequence with other ways and basically approximate this. You never, like, getting the most likely sentence is an impossible problem. I mean, I don't know, NP problem or something. Yeah, it's NP. So, anyone has an idea? Oh, the most naive thing you can do is say, okay, if I want all my sentence to be likely, just when I get to predict the first word, I'm just going to take the likeliest one, use that as my input, feed the next step, take the likeliest word, etc., etc. There is no particular reason that you are going to get the most likely sentence if you do that, sequence, I mean. But it's hopefully it's going to be not so bad. So it's called greedy search because the idea behind it is just a greedy algorithm where you, at each of your steps, you take the thing that that seems the least stupid to do, and you hope that the whole result is not stupid either. So it's called an inference method because that's how you deal with inference means like use that you use your model to actually infer an output in an approximated way. It's not very good. We're gonna see right now that it's not very good. So I didn't retrain everything. I just used what I did yesterday evening, but you can do that by yourself. So here I just a little function to generate where you get this is the seed, so the beginning of the sentence. So you transform that into integers, into a tensor on the GPU, feed it to the model, and there is I feed it to the generate function, which is going to return a sequence of integers, and from that I get text. So just to show you the generate function, it implements the greedy search that I just mentioned. So the beginning is pretty much the same as here, except sequence is actually just one sequence. I didn't do that for batches. So I have to add the batch dimension myself. I get when I feed that, I get the output of the LSTM, the scores. But actually, the only thing I'm interested at this step is the scores for the last word. When I fed the last word of the sentence, so that's what predicts the first word that I'm generating. So that's the output, the scores, and the words that I'm using is the argmax of that. So torch.max, I don't know if you used it, but the first output is the max and the second is the argmax. So I take the second, and that's the words the first word I generate. So here I stack all the generated words, So that's one. And if I want to predict more than one, I just use my current word as the next input, take the embedding, take the LSTM. So I just feed one thing to the LSTM, but I need to use the hidden state. That's one case where you use the hidden state. The hidden state I have to use with the RNN is the one that was outputted by the network at the previous step, because this time I can't rely on the RNN class to do itself. I take the output, I take the argmax, and I feed it at the next step. So I have to do that one step by one step. Yeah.
So can you just diagram out, like we're trying to generate predictions, the most likely word at the end of this, after a sequence, correct? And so my understanding is you're feeding it in layer, like word by word, to get the most likely word from the RNN. How is this process working? I'm just not following the code as well.
Oh, it's the code or it's the idea that you?
Probably the idea.
Okay.
What I'm not following completely.
No, actually, I'm gonna if I go back on the slides, I'm just gonna use this one.
Okay.
Yeah. So let's say you have 4 words in your sequence, and you want to predict the 5 next words, or 6, I don't know. So in this, how I change this diagram for this application is I just feed the first 4 words, which I have, and in the end, the first 3 things are like prediction of the next word, but I don't need that because I don't care. I just want to generate the next thing. But the last output is supposed to be, because that's what my language model does, is supposed to be the prediction for W5. So yeah, I take W5, the W5 the language chose, so the argmax, and I feed it back to the next step. And here, I'm just gonna feed back W5, get a prediction for W6, take the argmax to get my actual W6, feed it back, etc., up to the number of words that I want to generate. And like I said, it's an approximation of the most likely sequence that comes after W1 to W4. It is not the actual most likely sequence.
So if we know W1 through W4, why isn't it the most likely sequence? Like we're feeding in W1 through W4 into the network.
Yeah.
You were mentioning that like in order to get the most likely, we have to feed in all different combinations. All different combinations.
I tell you because let's say you just want to predict 2 words. Okay. So the first thing you do, you feed your n words, and you're gonna get, because that's what the output is, you're gonna get the probability of W5 given W1, W2, W3, W4. Can you follow the, yeah, perfect. So you get that. Yep. If you feed W5 at the next step, the thing you're gonna get is the probability of W6 given W1 to W5. The thing is, you didn't, when I take the argmax of this, I get the condition probability of W6 with respect to the W5 that I chose at the previous step. Okay. But I made a choice at this point. I choose the one that seemed the most likely for W5, but it's very possible that the second most likely, for example, led up to a probability that was much higher for the strongest W6. So like you could, for example, if you make a bad choice for W5, even if it was the most likely one, you can end up with all your characters being equally likely, and then your W6 is representing nothing at this point. Is that clear? It's so that's from the mathematical point of view. It is actually kind of clearer when we'll actually use the greedy search to see where it is the kind of mistake that it can make. Is the code clear apart from that? Okay.
And they're generating characters, just to be clear, right? So these are like...
In here, there are characters. There is literally no difference between words and characters in the way you use them, except that you have much more, the vocabulary is much bigger when you use words, and the sequences are much shorter. That's pretty much it. On paper, it's the exact same reasoning. You've got a sequence of stuff, and you feed this stuff.
Right. I think the main question I have is like words are usually variable length, and how do we guarantee that our RNN or our else team is not being?
Because I'm not feeding actual words. I'm feeding the integers that represent the indexes of these words in a vocabulary. So yeah. So if I go back. Yeah, here in my corpus, I read the corpus. So at this point, corpus is made of text. Here, I turned it into an array of integers. So if I look at the first 17 elements of this array, they look like this. So these characters represent the actual words. And if I use the toText method, I get back characters from these words. Is that clear?
Feeding characters then?
Hmm?
We're not feeding in words, we're feeding in characters, correct?
Here I'm feeding characters. I'm feeding integers that represent characters. I could feed integers that represent words. That doesn't make any difference from the network's point of view. You just have to use it to be consistent in your vocabulary size, that's all. So here, the network I use is completely unable to predict words if I extracted words because I trained it on characters. But I could use the same network to predict words. Just have to, here the way this map thing works is that it looks at all your characters separately. And if the character has not been seen, it associates it with an index. If you divide your text into words with by like splitting it with the space character, you can look at every word, and if you have not seen this word, you associate it with an integer, and it's basically the same thing. But the vocabulary size would be higher. Yeah, I know it's confusing because sorry about that. The slides do deal with words, but then the model does character, but like on the architectural level, it's exactly the same. For the rest of this loop is I do the thing that the iteration of the greedy search as many times as I want to predict words. And in the end, I just, iteratively, I append these to my generated words list. And in the end, I just concatenate all of these on dimension 0. And I get back a sequence. So let's see how it works in when I do it. So, yeah, so here I feed, like I said, I feed a sequence, like I extract to be a tensor, and I take back what I generate, transform that into an NumPy array, and use the method to convert it back these indexes into characters. And so if I use to be or not to be, that is the I kind of hoped to have question. I got queen instead. And that proves that the model is not pretty good because this is a sentence that's actually in the training set. So it could have learned to that sentence and overfit it to return question. It didn't because I didn't train it long enough. If I did like 1,000 epochs, it probably would have. But it still learned to generate an actual word when it had no information, no lexical information initially. So that's still something.
How do you make the dictionary? Do you map the words and numbers randomly, or?
I map characters to integers. I actually don't do that. It's my auxiliary file Shakespeare data that does that. I just use the get char map method, and basically it's gonna look iteratively at all the characters in order in the text. So the first one it means is 1. So it's going to associate 1 with an index, 6 with an index, etc., etc. Back to next line is also a character, so there is an index for that. 5 is going to be the space, I guess. And when you get back here, you have already seen space, so you don't add another integer. You just you already know this one. And whenever you meet a new character, you associate an index to it. That's all. It's not random. It's iterative, but it could be random. There's no difference. And okay. So here, when I just I try Richard as my seed, and I want to predict a lot of text. So a lot of different things can happen, but basically here, it generates a few words, and then it generates back to next line, and then it gets caught in a loop, and it only predicts spaces up until whenever. So that's one example of bad stuff that can happen with greedy search. Basically, if you're at a point where you've got a lot of, because of the way this data set is, you've got a lot of initial spaces at the beginning of every line. So if it learns a space character, it's likely to, after that, have another space character. So basically, you've got a loop where once you've predicted a space, at every step, you look back at the previous character, it was a space, so most likely thing is also a space, and you end up having only spaces. So that's bad. Another thing that can happen is you just have a repetition of words. That depends what kind of data set you have. I could have preprocessed this data set to remove the spaces, but I didn't want to do that because hopefully it could have learned to do text that actually is structured like this. It didn't. All that to say that greedy search is not super good. So I believe in homework 3 part 1, you're going to have a task to actually generate text. And you're going to have to do something that's a little better than greedy search if you want to have a good results. So a couple of other possibilities that you can do to generate text. First, you've got something called random search. What? Okay. I'm going to try to do that pretty quickly. So in random search, instead of taking, when you arrive to your probabilities for a word, instead of taking the most, the argmax of this, you can, this is a probability distribution. If you just softmax it, you get a probability distribution, and then you can sample from this distribution. So you get a word that has the same probability as its output. So kind of like a greedy search, the words with the highest probability are going to be the likeliest one that to be sampled, but they're not the only ones. You've got some randomness here. So there's no particular reason that this actually does better than greedy search, but there's one major difference, which is that this is not a deterministic process. It's a stochastic one. So if you do it several times, you're going to get different results. So if you do it 100 times, you're probably going to get at least one thing that's better than greedy search. So that's kind of why it's useful. Yeah.
So we're just saying we're getting a higher probability of word 6 because we selected several.
Here, yeah.
You put in the word 6.
Come on. So when you arrive here, what you get is a vector. Let's say you softmax it, you get probabilities for all of the candidates for W5. So here I took the one with the highest probability. But in random search, I just sample words from this probability distribution. So yeah, the argmax one is gonna be the most likely to be selected, but it's not the only possibility. And in particular, if you have a couple of likely words, if you do this process 100 times, you're gonna select both. So if one happens to be much better for the prediction of everything else, you're gonna meet it at some point. So that's kind of why random search, if you do it once, it's not very good. If you do it many times, and you look at, you can look at the probability of the whole sentences many times. So it's kind of an approximation of the thing I said when I said you have to try all of the sentences to know which one is the likeliest. Here you don't try all of them, but you try a lot of them that you sampled through these probabilities. An interesting property is that when you do that, the probability to get some sentence is exactly the probability of this actual sentence. Because of at every step you generate the probability W5 from its probability condition of the previous words. So the probability of a sequence is the product of all these conditional probabilities, which ends up being exactly the probability of the sentence. So that's pretty good because then if you do that 100 times, you select from the probability, the distribution over sequences, 100 sequences, and hopefully the likeliest ones you're gonna select all of the likely ones, so you can know which one is the most likely. So that's kind of the idea behind random search, which is fairly easy to do as well. So it's a thing I recommend. But the one you see most in all of the papers about text generation is beam search. So beam search is pretty much the same principle as greedy search, except instead of taking D1 argmax at every step, you keep the n best ones. So let's say 10. So at every step, at step 1, you take the 10 best candidates for W5. And at the next step, you're gonna try all of these probabilities. So you'd get the 10 best ones for W5-1, 10 best ones for W5-2, etc., etc. So you end up with 100 sentence sequences. And from this, you prune back to keep only 10 as well. And so you kept the 10 most likely out of 100. So at every step, you generate a set of likely sentence sequences, and you keep the likeliest one. So that's probably the best algorithm. It's also not so easy to do, actually, especially when you have to keep a set of all the hidden states, etc. So it's a great algorithm, but you do that in last when you're pretty sure that your model actually works. Is beam search rather clear? Yeah. Yeah.
So, follow-up question on the application. So, like, is there like so we kind of talked about the text prediction.
Yeah.
But like getting the next couple words of your model, is there a good industry application other than just like generating more Shakespeare text?
I mean, not with Shakespeare text, but if you trained a language model on actual messenger messages, see if you're Facebook, when the guy tries to predict starts writing a word, you feed the beginning of this word or the sentences before, and you keep generating characters until you get to a space. And when you get to a space, you know that everything that was before was the whole word, so you can just suggest that.
Could this work for chatbots, like where you're feeding in questions and it's outputting answers, or would that be very difficult to?
Okay, well, that's part of what is used in chatbots, but chatbots are also like there is a very, very large set of NLP code dialogue with a lot of stuff in it, and it's very complicated. And this is a very little part of it, but yes. Well, that's pretty much for language models. Don't leave yet, because we're actually not so done. There is one thing that I did at some point that was kind of not a great thing to do when you do RNNs. So let's just go back on that. You know, when I said how you divide your text to get your batches, I said like you got one big array of text. You just take all your length L sequences. So you can do that with a language model. The thing is, I did language models not because we all want to do language models all the time, but because they're a pretty easy example of how to use RNNs. And the thing is, in other applications of RNNs, you're definitely not going to be able to do that. The reason is, let's say you're doing translation, for example. Let's say you're doing translations. So you've got a sequence like, I don't know, I like apples. That's your X. And you've got also your labels that are the translation of that, which is j'aime les pommes in French. If you ever do translation, you're going to notice that all the examples are French to English or English to French. And that's absolutely awesome if you're French. So the thing is, if you do that, here you've got a 3-word sentence if you do words. And if you do character, you've got I don't know how many characters. But you can't just take chunks of this and feed it to your RNN. We're not doing translation today, but if we were, you know that you have to deal with the input as it is. You can just take a sequence of it and deal with it. If you take the first half of the sentence, you don't know what part of the labels are predicting that. Basically, you have to deal with the inputs as they're given to you. So you have to do variable length RNNs. So like I said, with language model, it's not so useful, but we're kind of going to make it useful. But in general, you're definitely going to have to do that, in particular with homework 3 part 2 when you do CTC stuff and decoding. So now you have, let's say your data set it's not a big set of text, but it's a list of sequences, and each sequence has a different length. So how do you fit that to your RNN? Padding is one idea. There is a simpler one. We're going to go to that. So if the first thing you might want to try is just avoid the problem and not do batches at all. So you can use batches of size 1. It is working. So it's the simplest thing you can do. And if you have to write a model, it's a very good thing to do in order to debug your model and until you're sure that it's actually learning. The thing is, it's super slow. So you would not want to do that up to in your actual training. You actually want to have batches. So another thing you can do is you take your list of sequences, and you, for example, you can extract from these all the sequences of size 5 and create batches just with sequences of size 5. So that would be like you look for sequences of the same size and you do your batches with that. So that's not a bad idea either. The problem is if you're in one of the cases I mentioned before where you've got like an input and an output sequences and they're not of the same size, then you're going to have a problem because even if you have found the inputs of same size, you have no guarantee that the labels will have RB sequences of the same size either. So you're going to end up with having the same problem. So this is, when you can do it, it's a good idea to do it. But in many applications, you cannot just rely on that. So next one was, you said padding. Yeah. So you can pad your sequences. The thing is, contrary to say homework 2, part 2, where you can just pad with the beginning of the frequencies to get back text. In homework 2, part 2, you're not interested in the sequence. You're just interested in patterns that identify the speakers. But in general, you are interested in the sequence. So you can't pad in a good way. So you have to pad in a bad way. But the thing is, if you pad in a bad way, you feed that to your network, and in particular to the RNN, and then the hidden state is doing stuff with this noise that you fed as your padding. And if you try to backpropagate on that, you learn randomness. So and you end up not learning very well. So just padding is not a very good idea. But when you pad, you can before you backpropagate, you can remove all the elements that have been predicted thanks to the noise. Just zero that and not use it in the actual loss, so that when you backpropagate, you're gonna learn on everything that you did except for this noisy part. So that's not so easy to do, but it's actually one of the good ideas. So you've got PyTorch provides you with like a pad sequence method that we're going to see later that can help you with that. You still got some problems with that. One of them being if you pad, you end up with like a batch where with like one inputs of one of the dimensions would be the length of your longest input. So if you had one big sequence, you end up with like one very big matrix to manipulate, and you can end up with unexpected out-of-memory error at any time. First problem, and also even if you don't, you're wasting a lot of computational power feeding zeros or anything to your network. So also a problem. That being said, it's still a pretty good idea, but you kind of have to be careful to when you use it. If you know that you have long sequences, you might have to reduce your batch size. But that is one idea. Now, another thing you might want to do is just feed the network with what you want to feed it with. Like, I'm just going to make, let's say you have a batch that's like this. So you've got like a batch of 3 elements. You've got one long sentence, one medium sentence, one short sentence. One thing you can do is you try to feed your RNN with first that, and you get an output for that. Then you feed it with this block, and then you try to stick them back together to get the output of the good shape. And finally, the last one, and you do that as many times as you have rectangles in your set of sequences. Now, the thing is, if you try to do that, good luck. It's not a trivial thing to do at all. But there is one good thing, which is that PyTorch already did that for you, actually. So that's called packed sequence. I don't know if you've met that before. Oh, 10 minutes to do packed sequence. Cool. Yeah, so some guys at Facebook did that, so now you can do it too. So you've got a whole wrapper around tensors that's called a packed sequence, and you can feed that to your RNNs. And that's actually probably the most advanced thing you can do in PyTorch to deal with variable length inputs. The thing is, it's you cannot. There are a couple of problems with it. I mean, minor problem is you can do that just for the RNNs. So when you get out, you have to retake the padded output to feed that to your linear layers and everything. And so you still end up at some points with two big matrices, and you are not completely free of the probability of getting an out-of-memory error, but it's still much better than with using padding everywhere. And the one problem is the large problem is that it's not completely easy to do, because you notice that here to have rectangles, that's exactly what PyTorch is doing. So, but to have rectangles, you first have to sort your sequences. You have to have the biggest on top and the shortest at the bottom. So you have to sort that. You have to remember that you sorted, and it's not so easy. But if you are careful, that's probably the best method. So in the end, when you're sure your model actually works and you've done batch size 1 and everything, try to implement that. Now, pad and packed sequence. Okay, a couple of minutes. 8 minutes, cool. So that's how you pad a sequence. That's not a specific type at all. It's just you get a tensor with zeros in it. So you give it a list of sequences of variable length. So here the length is where 1, 4, and 3. So you see that in the padded version, the first dimension ends up having zeros for the steps 2 to 3, and the last one has zeros too. It's just padding basically. So but it's still pretty useful to have something that to do padding for you. Packed sequence are a little more tricky, just because, like I said, you need to give it the RS sorted by length in decreasing order for it to work. So you use the packed sequence method. All of these are in torch.nn.utils.rnn. So if I give it the list of sequences in the sorted order, it returns a packed sequence, which is a wrapper for your tensors that you can feed into RNNs. You can go from padded to packed and from packed to padded fairly easily. Thing is, when you go from padded to packed, PyTorch cannot know which of your, you just give it a tensor, so you can't know the length of your different sequences. So you have to tell it to tell PyTorch. So you keep track of the length of all of your sequences, and you feed when you create a packed sequence from a padded sequence, you give it the padded and the length. And when you go back, it's going to return the padded tensor and the length. No RNNs. Like I said, packed sequence can go directly into the RNN modules, but that's all. You cannot give a packed sequence to a linear layer or a convolutional layer. So you have to jump between packed sequence and regular tensors all the time. So I made the second version of the language model, but this time with packed sequence. Yeah, you can see it. So just to say that I actually need them, instead of using one big array for the Shakespeare data, I do it line by line. So all the sequences of characters in the data set are going to be the different lines in the Shakespeare data set, trimmed this time with from the spaces. So if you had a line with only spaces, it's removed, and if you had like a lot of spaces at the beginning, it's trimmed. Text to shade. It doesn't look very trimmed actually. Not good. Okay, never mind. Maybe it's not trimmed. Never mind. So another version of the data set, this time dealing with lines. So it's not, we can't return a batch. In the collect function, we can't return a tensor, so we're just gonna return a list. So I store the list of all lines in the form of tensors, and when I get to return one, I just take the output. This time, the sending them to CUDA if needed is done in the lines dataset class, because it's you can send a list to CUDA. So if I were to do that afterwards, I have to iterate over the list to send everything to CUDA, and so just doing it now is faster. And in collate function, I do the actual sorting. So here, it's not so difficult because you don't have to sort to go back to the unsorted order. So I just keep track of the lengths. The other good thing is that the targets are the same length as the input, so that makes things easier. So I just take the lengths, get my new order from the sorted lists of lengths. So just one formula you can do. So that just returns the arg sort of the list of lengths in decreasing order. So that's pretty useful. You can copy it directly from in your homeworks. And these are the sorted inputs. These are the sorted targets. Now the packed language model is exactly the same thing as the previous language model, with just one difference, which is I know I'm dealing with I'm feeding the forward loop with forward method, with a list of sequences. So when I want to use a linear or an embedding or something like that, I take the 2D version. So I just concatenate all my sequences. And when I want to feed it to an RNN, I take the packed sequence version. So that's a little hard to track. So that's kind of the problems with packed sequence. You have to be careful. So usually you need two things. You need the list of your lengths, the length of all your sequences, and you also need the bounds of each sequence in the concatenated version. So that's what this bounds list is doing. So you see that when this is the concatenated version, I feed that to the embedding layer. To get back a list before packed sequence, I use the bounds list. I get back my list of sequences. I can give that to packed sequence directly. Feed that to the RNN. And I get my padded output. You can't get back a list of sequence from packed, as far as I know. Maybe you can. But for what I know, you can just get a padded sequence with the list of lengths, which is just the same as here, so I don't need it. And from this list of lengths, I can get back the concatenated version of the output, use that for the scores, and I return this time directly the flattened scores. The generate method doesn't change. So the one good thing in all this is that you can use the same RNN class to feed sequences and batches and packed sequences. The only condition is that you have this time to use the batch first equals false. It's not an option. So we don't need to look at generate. Now in train epoch, so not that many things changed. The one big thing, so in the criterion, target is a list, input is a list, output is already flattened. So I just flatten targets 2 in the criterion. Now, the one thing that's important is that you're dealing this time with variable length sequences. So when you train, you want to take that into account because the longest sentences are like the ones you want to get the most learning of. So because how to say it? Yeah, as many. Yeah, when the sequence is long, basically you want it to impact more on the learning than when the sequence is short. So the one way to do that, the simplest, is when you do cross entropy loss, you can give it the attribute reduction equals sum, when by default it would be reduction equals average or something. So instead of taking the average of the 2D input that you give it, this time the criterion is just gonna sum everything, and you can use the sum as your to do your gradients on. But when you look at the loss per word, you have to be careful of that and divide by the number of all of the words. And well, apart from that, it's pretty much the same. So I just did one epoch this time because there are more sequences than before. It's a bit longer. So I get a pretty good how to put it, perplexity. But the model is not particularly better. One thing that I changed, yeah, I forgot to say that in the generate function of the model, because that's kind of what we were saying earlier, actually. Because I feed it with only lines that end up with the end of line character, the model is trained to deal with this kind of sequences. So I took that into account in the generate function, and I said it, if you end up with an end of line, so that's the stop, the character name stop, I just pass it as a parameter to the network. Then you end the iteration here. So in the generate function, you can see here, it went back to line and it just stops. Is that all clear? Because if it's not, I mean, it's kind of hard to look at the code when there are packed sequences involved. So that's kind of why you had to see it once before you have to do it yourself. Apart from that, I think we're good. So the next thing you're going to see with RNNs are CTC decoding, which is going to be useful for homework 3 part 2, and attention in encoder-decoder models. That's going to be very useful for homework 4. And that's all. So if you have questions, you can go. Oh, almost there. Yeah.
The recitation next week, isn't it the day off? Isn't it supposed to be great?
Was there any information about that? Because if not, if there is, I'm not aware of it. There should be a recitation, yeah. I mean, what did you hear?
Our college announced that there would be no classes that day.
Oh, I did not know that.
Our college, I meant Heinz College.
Oh,
I think it's CB-wide.
I don't think.
But I just know that I know that they announced us.
oh, cool.
There would be no classes that day.
Well, the thing is, you're kind of gonna need the recitations, so I don't know what we're gonna do. I think most likely thing the recitation is gonna happen, and if you don't want to come and watch the video, I guess that's fine. But yeah, I don't know. Maybe if it's CMU-wide holiday, maybe we're just not allowed to use the classroom. Okay, we'll figure something out. Thanks for warning.